Let's have this example. A rectangular reinforced concrete beam has a dimension of 250 mm of its width. Then the height is 500 mm and the effective depth is 400 mm. It is reinforced with a 25 mm diameter tension bars and simply supported with a span of 12 meters. Calculate the maximum concentrated live load that can be applied at midspan if Fc prime is equal to 21 megapascal and Fy is equal to 345 megapascal. So first, we need to illustrate the problem. So this is your beam. The width is 250 mm and the height is equal to 500 mm. Since this beam is a simply supported beam, the tension is at the bottom. So your tension bars will be placed at the bottom. So this is the D from the center of centroids of your bars to the extreme fiber of your beam, that is your effective depth, which is equal to 400 mm. So this beam is a simply supported beam, so we assume this is the figure of your beam, and your beam is uniformly loaded for the entire beam span, and you have there it is assumed that the live load is at the midspan. So we'll let that as PL, and this is your weight of the beam, which is kilonewton per meter, or kilonewton per meter. Okay, the length is equal to 12 meters. Okay, so next we have to list all the given. So the properties for the compressive strength of the concrete is 21 megapascal, and Fy is equal to 345 megapascal. Then we have to calculate the maximum concentrated live load. So that is your problem. Okay, so first we have to get the area of the steel bars, because our steel bars is 825 mm diameter. So we have 8 times pi over 4 times 25 square. So this is equal to 3927 mm squared. So we have to check. We have 3.1416 divided by 4 times 8 times 25 squared. So 3927. Okay, for the beta 1 or the beta factor, we have the formula 0.85 minus 0.05 divided by 7 times Fc prime minus 28. So we have to substitute the value of Fc prime to our formula. So we have 0.05 divided by 7, 21 minus 28. So beta 1 is equal to 0.85 minus 0.05 divided by 7 times 21 minus 28. So this is equal to 0.92, and this is greater than 0.85. 0.85. So, use beta 1, which is equal to 0.85. And since also your FC prime is greater than, no, FC prime is less than 28 megapascal. So your beta 1 is equal to 0.85. Okay, so next we have to assume that our Fs is equal to the Fy. So assume, this is our first assumption. We have to assume Fs is equal to Fy, and that is 345 megapascal. So again, we have to check that is 345 megapascal. So to get the depth of the compression block, that is A, which is equal to ESFS over 0.85 FC prime B. So you have the area is 3927 times 345 divided by 0.85 times 21 times B. The width of our beam is 250. Okay, 250. So A is equal to 3927 times 345 divided by 0.85 divided by 21 divided by 250, and that is equal to 303.6 meters, sorry. Okay, so I have to add this one. We designed this using USD method. Okay, then we solve this problem using USD method. Okay, so we have C is equal to A over beta 1, that is 303.6 divided by 0.85. So your C, 303.6 divided by 0.85, so you have 357.176 mm. And that is the location of your neutral axis from the extreme fiber of your concrete in the compression side. Next is we check if our assumption is correct, no? By checking the strain of the steel bars. So we'll compare the actual strain of the steel bars to the yield strain of steel bars. So we have here for the yield strain of steel bars, we have strain is equal to Fy over Es, and that is the modulus of elasticity of the steel. So we have 200,000 megapascal. So the answer is 345 divided by 200,000, and that is 1.725 times 10 to negative 3. So this is 0.00175. Okay, next is the actual strain of steel bars. So we have ES is equal to D minus C over C times 0.003. So we have this formula. So your effective depth, again, we will check. Okay, that is 400. So 400 minus the C, that is 357.176 divided by 357.176 times 0.003. So the actual strain of steel bars, so you have 400 minus 357.176 divided by 357.176 times 0.003. So this is equal to 3.5968 times 10 to negative 4. So we can write this as 0.00036. Okay, so we have to compare this to the yield strain, and this is less than of the yield strain. So we can say beam is over reinforced. So for beam over reinforced, your Fs is not equal to Fy. Therefore, our assumption is wrong. Okay, so first we assume that the Fs is equal to Fy, and it is not equal. So this assumption, okay, that assumption is wrong. So again, since the assumption is wrong, Fs is not equal to Fy, so we have to find the correct value of our C, because the C was determined because we assume Fs is equal to Fy. So since it is not equal, so we have to solve again the value of the C. So we will start for the equilibrium condition. C, the compressive force of the concrete is equal to the tensile force of the concrete. So we have this 0.85 Fc prime AC, that is equal to ES times Fs. So here we have 0.85 Fc prime. The area of concrete is equal to the depth of the compression block times the width of the concrete, which is equal to the area of steel. Then Fs there is equal to the strain, the actual strain of the steel bars, times the modulus of elasticity of the steel. So we have this one, Fc prime, 0.85 times Fc prime. Our A is equal to the C, that is the distance from the neutral axis to the extreme fiber of the beam in the compression side, okay, times beta 1 times B, and that is equal to AS. Then for the strain, okay, we have this formula, ES, and that is D minus C over C times 0.003. So I have to write this again. So we have D minus C over C times 0.003. That is the strain, the maximum strain of the concrete, times ES. Or we can have this formula again. We have times EC. Okay, then ES. Then we substitute. We have 0.85 times 21 times C times your beta 1 is 0.85. Your B is 250. Your AS is equal to 3927. 3927. Then D is 400 minus C over C. Okay, times 0.003 times 200,000 for our modulus elasticity of our steel. So here we have to compute. For the left side, you have 0.85 times 21 times 0.85 times 250. So this is equal to 3793.125 C. And this is also equal to 3927 times 0.003 times 200,000. So we can say 200 times 400 minus C over C. So we have now this equation. Then again, we have to simplify this one. So we can transpose the C to the left side. So this will become 3793.125 C squared is equal to 2356 200 times 400 minus 2356 200 times C. Okay, so I hope I don't miss anything for this equation. Okay, so we have this one. You can simplify this, and this is in the form of a quadratic equation. So we will try. We have this one. I like to simplify this. We can say this is C squared. Then we divide it 2356 200 2356 200 times 3793.1, sorry, that is divide 2356 200 divided by 3793.125. So this will be minus plus 621.176. Okay, then minus 2356 200 times 400 divided by 3793.125. So this will be equal to 248,470.588. That is equal to 0. Again, we have to check. Okay, 2356 200 divided by 3793.125. So that is 621.176. Okay, C. 176C. Okay, that is positive. 2356 200 times 400 divided by 3793.125. 248,470.588. So this is in the form of quadratic equation, you can solve it using the formula of quadratic equation, or you can use your calculator. You can use the shift solve, then you can go to the mode, then you have mode 5, then that is 3, then you have for the c squared you have the value of 1, then you have positive 621.176, then you have 248470.588, and that is equal to 0. So you can get directly the value of your c. So c is equal to, I missed the sign. That is negative 248470.588. So the answer is 276. So since this is the power of 2, so you have 2 value of your c. So the other one is negative. So the answer is 276. I got wrong. 27. Again, we have mode 5, then 3, then you have 1 equals 621.176 equals, then you have, don't forget the negative sign, 8470.588. Okay, you have 276.724 or the other value is you have negative 897.9, so that is impossible. So we don't have, there's no physical meaning of the negative value, so we use 276.724 for our c value. Then we can get now our a, which is c times beta 1. So you have 276.724 times 0.85. 0.85. So our a, okay, in getting the c, you can use shift solve, or you can use quadratic equation, or you can use your calculator for in getting the, and using the mode, mode 5 for the equation. So it's up to you how you are going to compute the value of c. So for the a, you have 235. Okay, this is 235.215 mm. So we will check 276.724 times 0.85, 235.215. Okay. So since we already have the value of a, this is now the correct value of a. Let's go to the nominal moment capacity. Okay, the nominal moment capacity of the beam. So, okay, nominal moment capacity. So this will be mn is equal to 0.85 fc prime ab times d minus a over 2. So this is equal to 0.85 times 21 times 235.215 times 250 times D is 400 minus A is 235.215 divided by 2. I have to write it again. So please remember the formulas we had derived the last meeting. So I hope you remember those formulas. I just directly write the formula in this example. So you have 0.85 times 21 times 235.215 times 250 times 400 minus 235.215 divided by 2. So that is 296. Okay, this is 296.412 times 10 to the 6. And the unit is Newton mm. Newton mm. Or you can say 296. Okay. Or nominal moment capacity is 296.412 kilonewton meter. Okay, so for the ultimate moment capacity, we just assume. So I try to assume phi there for the reduction factor, which is equal to 0.90. So you have mu. But we need to compute the value of phi. But in this problem, I am going to assume that the phi is just equal to 0.90. So we have here phi. This is for the ultimate moment capacity, that it's just equal to the reduction factor times the nominal moment capacity. So since I am assuming that your feeder is just equal to 90, so you have 0.90 times 296.412. So this is your ultimate moment capacity times 0.90. So you have 266.771 kilonewton meter. Okay, I have to check. 412 times 0.9, 266.771. Okay, so this is the weight of the beam. Weight of the beam, and this is in kilonewton. Okay, we have kilonewton per meter. So we have the dimension of the beam, so we can compute. Okay, weight of the beam, let's say WB. So you have 0.25 times the height. What is the height of the beam, or the depth of the beam? The depth of the beam is 500. So you have 0.5 times the specific gravity of the concrete times the specific weight, that is 9.81. So you have there 0.25 times 0.5 times 2.4 times 9.81. But 2.4 the specific weight of the concrete. So you have 2.943 kilonewton per meter. So this is the weight of the beam. Okay, so your beam is a simply supported beam, and the maximum moment of the uniform load is equal to 1/8 WL squared. So for a simply supported beam, the maximum moment for this, Okay, the maximum moment for this is equal to 1 over 8 W L squared. So we can say that the maximum moment of beam is equal to 1 over 8 weight of the beam times L squared, and this is equal to 1 over 8 times 2.943 times the length. Again, the length is equal to 12 meters. So you have 12 squared. So this is the maximum moment of the beam due to dead load or due to weight of the beam. So that is 1 divided by 8 times 2.943 times 12 square. So this is equal to 52.974 kilonewton meter. Okay, since the load factor of our beam, I mean for the dead load, is equal to 1.2, and the load factor for the live load is 1.6. So we have this one. Your ultimate moment is equal to 1.2 times moment due to dead load plus 1.6 times the moment due to live load. So we can substitute this. You have 266.771. So for the ultimate moment, you have 266.771. 266.771. So this is okay, 266.771. This is equal to 1.2. The moment of the dead load is also equal to the moment of the beam. So you have 52.974 plus 1.6 times moment due to live load. So for moment due to live load, you have 266.771. Okay, minus 1.252974. So you have 203, okay, divided by 6, divided by 1.6. Okay, equals 127.004 kilonewton. Kilonewton meter. Okay, 266.771 minus 1.2 times 52.974 divided by 1.6. Okay, again 127.001. Okay, that is the moment due to live load. So since the live load, it is assumed that it is at midspan. So we have there PL, that is 10. The maximum moment for this is equal to PL over 4. So we have PL over 4 for the maximum moment. Okay, so we can say the moment due to live load is equal to P times L over 4. So your concentrated load, this is at midspan, is equal to 4 ml over L. So we have 4 times 127.001, okay, 0.001 divided by 12. So P, so 127.001 times 4 divided by 12. So this is equal to 42.333 kilonewton, and therefore this is the answer. So you have to encircle or box your final answer. So this is what we need in this problem, we need to find the maximum concentrated live load, which is at the midspan. So this is the answer, which is equal to so that is equal to 42.33 kilonewton. So I hope you understand this problem, and thank you for your time.